Hello everyone. Today, we're diving into the three pillars of calculus: limits, derivatives, and integrals. Why do they matter? Because they help us understand and predict change, how things move, grow, or shrink. Calculus is the math of motion, not just static numbers. These concepts power real-world innovations. Engineers design bridges, economists model markets, doctors track medicine in the body, all using calculus. Let's start with limits, the foundation. Limits let us see what happens as we get infinitely close to a point. From limits, we build derivatives, which measure how fast something changes at a single instant, the slope at a point. Integrals do the reverse. They add up tiny changes to find totals like distance traveled or area under a curve. The beauty? Derivatives and integrals are deeply connected by the fundamental theorem of calculus. Mastering these ideas gives you a toolkit for solving some of the world's most important problems. Ready? Let's begin with limits. What is a limit? Imagine walking toward a wall, halving the distance each time. You get closer and closer but never quite touch it. The wall is your limit, the value you approach. In math, a limit tells us what a function's output gets closer to as the input nears a specific point, even if it never actually reaches it. For example, consider fx equals sign x2, 1, x, 1. Plugging in x equals sign 1 gives 0 zeroths, undefined. But as x approaches 1 from either side, the output approaches 2. So, the limit of fx as x approaches 1 is 2, even though the function isn't defined at x equals sign 1. Limits are about the trend, not the destination. This idea unlocks everything else in calculus. Limits let us handle situations where direct calculation fails. They're the bridge from algebra to calculus. Next, we'll see how limits help us define the derivative, the math of instantaneous change. With limits in hand, let's talk derivatives, the tool for measuring how things change in an instant. Think of your car's speedometer. It shows your speed right now, not your average speed. That's what a derivative does. Mathematically, it's the slope of a curve at a single point. We start by finding the slope between 2 points, then use limits to bring those points infinitely close together. The result? The tangent line slope at that point, the derivative. For example, if fx equals sine x2, the derivative is fx equals sine 2x. At x equals sine 1, the slope is 2. At x equals sine 3, it's 6. The derivative gives us a new function describing the rate of change everywhere. It's how we analyze motion, growth, and trends in science and engineering. Next, let's see how integrals let us add up all those tiny changes. Now, integrals, calculus in reverse. If derivatives break things down, integrals add them up. The classic use: finding the area under a curve, like total distance from a velocity graph. We approximate the area with rectangles, then use more and more, making them thinner. As the number of rectangles approaches infinity, their total area perfectly matches the curve. That's what an integral does. It's the limit of a sum of infinitely many tiny pieces. Integrals let us calculate totals, distance, area, volume, when things aren't simple shapes. The fundamental theorem of calculus links derivatives and integrals. They're opposites. Take a derivative, then an integral, and you return to your original function plus a constant. Limits, derivatives, and integrals form a powerful system for understanding change and accumulation. That's the heart of calculus and why it matters.